let's get into this. When you think about those military drones, the ones flying way up high, sometimes thousands of miles away, we see the videos, but like, how do they actually talk back to their controllers, especially over those huge distances? It's kind of hidden, isn't it?
It really is. And what's amazing, it's not just like a fancy radio link. I mean, the whole communication setup is incredibly complex. It's built for, well, extreme reliability, resilience, and maybe the most crucial part, security,
Yeah.
especially when others might be trying to listen in or, interfere.
Absolutely. And that's exactly what we're diving into today. We've got the source material you shared, and it focuses specifically on these communication systems, the frequencies these military drones use.
Right.
So our mission for this deep dive is basically to unpack the technical stuff laid out in the source. We want to understand the different ways they stay connected, look at the specific frequency bands they use for different jobs, and uncover the really critical security measures and, interestingly, the autonomous fail-safes built in. We really want to give you, the listener, a clear picture based only on what's in this source material.
And getting this communication piece right is just vital. I mean, without a secure, reliable, real-time link, both for sending commands to the drone and getting data back, like sensor feeds, telemetry, all that stuff.
Or useless, basically.
Pretty much, they're grounded, or worse, you could lose them.
Yeah.
That connection, it's not just a tech detail. It's really the core thing that makes them work in modern operations.
So it's fundamental. It's the whole game. Now, the source material seems to break down communication based mainly on distance, right? Like there are two main ways they do it.
Exactly.
Yeah.
First up is line of sight, or LOS. This is for when the drone and the ground control station are relatively close. Think typically up to maybe 150 to 200 kilometers.
Okay.
It's like being within a direct radio horizon, more or less. It works using radio frequency, RF signals, traveling directly between the drone and the ground station.
So for things like training flights or missions happening not too far from base.
Precisely. LOS is great for real-time piloting because the delay, the latency is super low. Plus, you get immediate telemetry, flight data, drone health, location, and you can pull down high-bandwidth sensor data like live video feeds.
And the tech for that.
The source mentions things like UHF, VHF radios, or sometimes more advanced microwave links if you need higher data rates.
Okay, right. That covers the local stuff. But what about, flying a drone over a completely different continent? You can't use a direct radio link then. The Earth curves, right?
Exactly. That's where beyond line of sight, or BLOS, methods come in. When the drone's operating really far away, truly over the horizon, or even globally, you need a way to bounce the signal.
Bounce it.
Yeah. The main method the source describes for the big military drones like the MQ-9 Reaper is satellite communication SACOM.
Ah, satellites.
Right. The drone talks up to a satellite orbiting Earth, and that satellite relays the signal back down to a ground station. And that station could be thousands of kilometers away from the drone and the satellite.
Wow, so the signal goes way up into space and back down. That sounds complicated.
It is, definitely. But it's how you cover those massive distances. And the source also points out, FTCOM isn't the only BLOS trick. Sometimes they use intermediate relay drones or other aircraft.
Like stepping stones for the signal.
Kind of, yeah. They act like flying repeaters. They grab the signal from the drone and then retransmit it towards the ground station, or maybe even to another relay. It extends the range or helps get around obstacles like mountains.
Okay, so we've got the how direct radio close by or bouncing signals off satellites or other relays for long distances. Now, the frequencies, where on the radio spectrum are these signals actually happening? The source mentions specific bands, but crucially notes the exact frequencies are classified.
Yes, totally classified. But understanding the general bands gives you a really good insight into the technical trade-offs they're making. The source brings up the C-band first. That's in the 4 to 8 gigahertz range, often used for LOS, line of sight.
Okay, C-band for LOS. Why that one? What's good about it?
Well, its main benefit, according to the source, is high bandwidth. That's really key for sending lots of data fast think, high-res video, detailed telemetry, stuff you need for close control and surveillance in real time.
Right, makes sense. Any downsides?
It does note a drawback. It can be more susceptible to weather, like heavy rain interfering with the signal. But interestingly, it counters that by saying compact antenna designs make it practical anyway for drones.
Interesting trade-off. High bandwidth, maybe a bit touchy in bad weather, but practical antennas. Okay, so C-band for closer stuff. What about the long haul, the satellite links?
For SACOM, the Ku-band is very common. That operates between 12 and 18 gigahertz, higher frequency again.
And its strength.
Like C-band, it enables high data rate transmission, but crucially, over those long SATCOM distances. The source specifically calls out its use for carrying live HD video feeds from operations happening anywhere in the world.
Wow.
And, importantly, the infrastructure is already there. It's widely supported by dedicated military satellite systems, like the wideband Global SATCOM, the WGS system.
Okay, so if you're seeing that super clear video from halfway around the globe, chances are it's coming via Ku-band STCOM. But what about the really critical commands? Just telling the drone what to do or getting its GPS data back. That feels like it needs maximum reliability, maybe less about huge bandwidth.
You've hit the nail on the head. That's exactly the trade-off. For command and control signal C2 and also for GPS, the L-band down at 1 to 2 gigahertz is often used.
Lower frequency.
Lower frequency, yeah. And the source really emphasizes its main benefit. It's much more robust. It's less susceptible to environmental interference, like weather, compared to the higher C or Ku bands. For those absolutely mission-critical commands or navigation data, reliability is king. It trumps pure bandwidth.
Right.
You don't need to stream HD video over L-band, but you absolutely need that turn left or go here signal to get through rain or shine.
That makes total sense. Choose the frequency that fits the job's priority. Any other bands mentioned for specific roles?
Yeah, the source also mentions S-band,
Wow.
which is between 2 and 4 gigahertz. It says it's sometimes used for telemetry and tracking. Its advantage is noted as being more resilient to interference than some higher bands, making it suitable for maybe more dynamic or mobile platforms.
So we've got C, Ku, L, and S bands, each with different characteristics suited for different tasks: video, control, GPS, tracking. And the source really stresses that while we know these general bands exist, the specifics, the exact frequencies within them, how they encode the data, the protocols they use, that's all highly classified.
Absolutely. And the why behind that is critical. It's explicitly stated to prevent adversaries from easily jamming the signal.
Like blasting noise at them.
Right, or intercepting the data, listening in, or even spoofing the communications trying to send fake commands or data. Security isn't just bolted on, it's woven right into the fabric of these systems.
Yeah, that tracks. If you can't find the signal easily, or can't understand it if you do, you can't mess with it. Speaking of security, the source goes into some fascinating techniques beyond just keeping frequencies secret. Encryption is obviously huge.
Oh, definitely. The source is clear. All data transmitted control signals, the drone's health updates, telemetry, the video, sensor feeds, everything is encrypted. They use military-grade standards, mentioning examples like AES-256 or even proprietary systems developed just for this.
So even if someone could somehow grab the raw signal...
It would just look like random noise, basically. Useless without the decryption key.
Okay, so the message itself is protected, but what about stopping the message getting through at all? Jamming.
Right. That's where techniques like frequency hopping, spread spectrum, FHSS come in. The source highlights this one, instead of just parking on one frequency.
Like a normal radio station.
Exactly. Instead of that, the signal rapidly jumps between hundreds, maybe even thousands, of different frequencies within its allocated band. It does this hundreds of times every second, following a complex pattern that only the drone and the ground station know.
Whoa. So it's like they're having a conversation, but shouting one word on 99.1 FM, the next on under 7.5, the next on 92.3, and changing faster than anyone else can possibly follow.
That's a great way to put it.
Yeah.
It makes it incredibly difficult for an adversary to jam effectively. They'd have to somehow blast noise across that entire wide range of frequencies all at once, or guess the hopping pattern, which needs some serious tech and processing power.
That is incredibly clever. The source also mentions something called low probability of intercept detection, LPI-LPD. How does that work? Is that related?
It is related, yeah.
Yeah.
LPLPD refers to techniques designed to make the signal hard to even notice in the first place. Hard for an enemy to detect that a transmission is even happening.
Hiding in plain sight, almost.
Kind of. Spread spectrum techniques like frequency hopping help because the signal's energy isn't concentrated on one frequency. It's spread thinly across a wide band, making it blend in more with background radio noise. Another technique mentioned is beamforming.
Beamforming.
Yeah, instead of broadcasting the signal out in all directions like a light bulb, the antenna focuses the radio energy into a very narrow, tight beam pointed directly at the receiver, like a laser pointer.
Much harder to pick up if you're not the intended target.
Exactly. Both these things make it much harder for an adversary's listening gear to even detect that a drone is communicating nearby.
Okay, so it's layers of security. Encrypt the data so it's unreadable, make the signal jump around so it's hard to jam, and make the signal itself hard to even find with LPI-LPD. But Even with all that, links can fail, right? What happens if a drone just completely loses contact with its ground station? Does it just fall?
No, definitely not. That's where the autonomous failsafes described in the source are absolutely critical, both for safety and for the mission. If that link is lost, the drone is designed to switch into an autonomous mode. It uses its own onboard navigation and pre-programmed instructions.
Like it follows a flight plan that was loaded up before it even took off?
Precisely that. It can automatically trigger a return-to-base procedure, flying itself back along a safe, predefined route to where it launched from. Or it might enter a holding pattern, just circling a designated area, waiting, hoping the communication link comes back up.
Okay.
It acts independently to stay safe and hopefully allow recovery of the drone.
That's a really vital safety net. The source also hints at more advanced autonomy linked to this, beyond just flying home.
It does, yeah. For the more sophisticated drones, the source notes they can use their onboard AI capabilities. So they're in a situation where communication is completely denied, the link is totally cut.
Jammed or just lost for some reason.
Right. The AI can potentially analyze the sensor data it's still collecting and continue parts of its mission autonomously. Maybe continuing reconnaissance, identifying potential targets, maybe even carrying out certain pre-approved actions based on its programming and what it's seeing in real time. All without that human link, at least for a while.
Wow, that's a pretty big leap. Continuing the mission without the human in the loop, even temporarily. It's fascinating how they balance that control and independence. Finally, the source gives a little peek into what might be next for drone communication, future trends.
Yeah, it mentions a few potential directions. Laser communication is one sometimes called free space optics.
Lasers, like sci-fi stuff.
Kind of. Using focused beams of light instead of radio waves could offer extremely high data rates. And because it's a tight beam of light, it would be very resistant to jamming and interception.
But maybe tricky with clouds or fog?
Exactly. It has its own challenges, like atmospheric conditions. The source also briefly touches on quantum encryption. The idea there is potentially achieving communication links that are theoretically unbreakable.
Quantum. Okay, that's definitely future tech.
For sure. And lastly, it mentions AI-enhanced networks. Using AI not just on the drone, but to manage the communication network itself in real time, dynamically choosing the best frequencies, routing signals around interference, constantly adapting to keep the link as strong and secure as possible.
Okay, so let's try and bring this all together then. Based on the source material we've gone through today, what's the main takeaway about how these military drones talk?
I think the key thing is just the sheer depth and complexity. It's not one thing, it's a fusion of different technologies, radio, satellite, maybe optical down the road. It strategically uses different frequency bands, C, Q, L, S, each picked for a specific job, whether that's high bandwidth for video or rock-solid reliability for commands.
Right.
And then, layered underneath all of that, are multiple overlapping security measures and backup systems. You've got the encryption, the frequency hopping, the low detection stuff, and those crucial autonomous fail-safes. It's all designed to make sure that link works and stays secure even when someone's actively trying to break it.
It really drives home that getting information to and from these drones isn't simple. It's this constant, really sophisticated effort against distance, against the need for more bandwidth, against weather, and critically, against deliberate threats from adversaries. And while we don't know the exact secret sauce, the classified details, understanding why they need these different modes and frequencies and how they build in all that security and redundancy, it really gives you a much deeper appreciation for the engineering involved in these platforms. They're vital tools, and this shows why.
It certainly does. And, thinking about where the source points at the end towards more autonomy, AI managing networks, drones potentially operating disconnected for periods, it does leave you with a pretty provocative thought, doesn't it?
Like what?
Well, what is this growing reliance on intelligent systems that might have to operate independently when that link is challenged or cut? What does that imply for the future of remote operations? How do you balance human control with machine autonomy when that tether, the communication link, isn't guaranteed? It makes you really think about the evolving nature of control itself in warfare and surveillance.